Okay, so thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Mehdi Soleimanifar from Caltech, who will tell us about certifying almost all quantum states with a few single qubit measurements. So for just a brief introduction for our speaker, so he is an AWS postdoc scholar at the IQIM in Caltech. So this is basically hosted by John Preskill and Urmila Mahadev. He obtained his PhD in MIT in 2022 under the supervision of Aram Harrow. And his research is mostly on the interface of quantum information and quantum computation, many-body physics, and theoretical computer science. So, Mehdi, the floor is yours.
Yeah, thanks a lot for the introduction, and thanks for inviting me. Thanks everyone for coming to my talk. So this is based on joint work with Robert Huang and John Preskill. So this is the problem. The problem is quantum state certification. And here's the setup. We have some n-qubit state. We call it rho, or the lab state. You can think of it as prepared or synthesized in an experimental setting. And we can actually prepare multiple identical copies of this state. And we can perform measurements on them. We also have a target state, which is an n-qubit n-qubit state, psi. It's a pure state. And we are given a classical description of this state. And by that, I mean there's some sort of classical model, which as input takes an n-bit string x, and then it outputs a complex number that we are going to interpret as the amplitude of the target state psi in the basis vector x. And so in other words, we're going to say we have query access to the amplitudes of the target state. So later on, I'll show you what exactly I mean by such a classical model, but let's just fix that for now. So having quantum access to the lab state and classical access to the target state, our goal is to determine if the lab state is close to the target state or not. Or more formally, we want to know if the fidelity or the overlap between these two states is close to 1 or is far from 1. So this is called the quantum state certification. And it's going to look at primitive quantum protocol, which many...
Sorry, I don't know if I should interrupt now or later.
Yeah, go ahead.
Well, I already interrupted you. So for this problem, you're assuming that because you want to be able to make many copies of the state. So is it sort of like you're having an IID assumption of some sort?
Yeah, so you assume that you have IID access to the lab state. If you want, you can think of like some quantum device that's preparing this state. You push a button, it gives you this state. You measure it, you push a button, it gives you a fresh copy, and then that's how you gather statistics.
Okay.
All right. So So this has many applications. One is in benchmarking quantum devices, in optimizing or training quantum circuits to prepare some target state psi, and to do tomography or learning on quantum states to learn their classical description. So later on, I'll go through each of these examples and give you a sense of how state certification enters the picture. But for now, let me just set up the the goal for the rest of this talk. So ideally, what we want is a certification procedure which uses very few copies of the lab state. And on each of these copies, we only need to perform simple measurements. Let's say single qubit measurements, things that are experimentally friendly. And on the target state side, we'd like to only make few queries to the amplitudes of the target state. So we only want to look up certain number of amplitudes, which is not a huge number. And gathering all this data from the target state and the lab state, we'd like to be able to efficiently process this data and then answer the state certification problem. And furthermore, we'd like this certification procedure to apply to arbitrary states, both in the lab and also target states. So, given this list of maybe contradictory demands, it's not very clear if there exists such a state certification procedure at all. So to give you a sense of what's been done before about this, let's kind of go over the previous approaches that people have considered. And the kind of the naivest thing you can think of is that suppose I know the circuit U that prepares the target state. So remember that the target state is just classically described to us. Suppose we know how to prepare it quantumly. Then one very simple way you could think of that you certify that the lab state is close to the target state is to perform the inverse of the circuit on the state row and measure all the qubits. And if you get all zeros, then that means you've recovered the state psi. So there are other variants of this. You can think of performing the swap test between the lab state and the quantum version of the target state. But in either cases, there is an apparent problem, and that's the fact that we need to apply this quantum circuit. Well, first of all, you need to find it, because as I mentioned, we are only given a classical description of the amplitudes of the target state. We have to somehow figure out a circuit that prepares it. And once we have that, we have to apply that circuit or its inverse on the lab state. So for a typical n-qubit quantum state, such a circuit U could be highly complex, could have exponential circuit complexity. And obviously it's something that we'd like to avoid. We're going to look for much simpler state certification procedures. And indeed, there are approaches that kind of get around some of these issues. And one is classical shadows, to use classical shadows. So this is a set of techniques that my co-authors have developed in the past. And here you've basically got two options. The first option is, instead of this circuit U in the previous slide, you apply a random Clifford circuit on each copy of the lab state. And then you measure all the qubits in the computational or standard Z basis. So this is the measurement part. And then there is a post-processing part that you use this data along with the classical description of the target state to see if these two states are close or not. So one problem with this approach is that it requires applying random Clifford circuits. And in general, these are deep circuits involving random gates, which may not be experimentally friendly. So I should say that since our result, there's been new advances on this problem, and in particular, now there is a way to kind of remove this random Clifford and replace it with a shallow circuit, which implements a unitary 2 design in logarithmic depth. And that would bring down the experimental demand. But even with that, there's still an issue with this approach, and it's that the classical post-processing part, where you take the measurement data and analyze it with respect to the target state to find the overlap, it's costly. It involves finding the overlap between the target state and a random stabilizer state, which isn't something you can do easily. So this is option one with classical shadows. You can also think of applying random Pauli measurements instead of the random Clifford circuit. So here, the experimental side is much easier. You're just performing single qubit measurements on each copy of the lab state. And these are random Pauli X, Y, or Z measurements. And then again, there's a post-processing part that you kind of analyze this data with respect to the target state. The problem is that the number of copies of the lab state, the number of samples you need for this procedure to work, scale exponentially with the number of qubits. So even though the measurements are simple, you have to repeat them exponentially many times. So again, this is not kind of something we like. And so these are rigorous methods. There's also a host of heuristic methods for addressing the state certification. And most famously, you can use the cross-entropy benchmarking. So this is a scheme that, for example, has been applied to analyze the quantum supremacy quantum supremacy experiment by Google. And again, it involves only measuring all the qubits with single qubit measurements. And these single qubit measurements are very simple. There's all z-basis measurement. So once you have this data, then you calculate this cross-entropy benchmarking score, which entails, finding the, let's say the measurement outcome of measuring all these qubits is an n-bit string z. Then you compute the overlap of your target state with this product state z, which just means looking up its amplitude. And then you kind of average over that for many copies, and that would give you something proportional to the XEV. So as you see, it's a very simple scheme, both experimentally and also the post-processing part is very simple. The problem is that it's heuristic. It's known to work in certain cases that I'll show you later, but it's also not hard to see that in general, it shouldn't work. It's kind of ignoring all the information about the phase component of your amplitudes. It's solely, relying on the magnitude parts. And indeed, it's not hard to come up with counterexamples where two states, rho and psi, are far from each other, but they seem to be close from the perspective of this particular benchmarking. There are also other methods that use single qubit measurements. They're very, very simple, but they only work for special families of states. Things like hypergraph state, the output of what's called the IQP circuit, or some sort of Gaussian state. And you can think of, roughly speaking, you can think of these states as families of low entangled states. So these are things that we know how to certify with Pauli measurements. Okay, so to summarize, the previous approaches to this state certification either require applying deep quantum circuits, or if they were using single qubit measurements, they needed exponentially many of them, or they were heuristic or restricted to kind of special families of not highly entangled states. So going back to my original goal, you can ask again, can we actually certify all quantum states with the least quantum and classical resources possible? Let's say single qubit measurements, few of them, and efficient post-processing. Is this possible or not? So this is where our result comes in. Maybe I should pause here if there are any questions. Okay, good. So this is our first result, which says that for almost all n-qubit states, n-qubit target states, you can certify its overlap with an arbitrary lab state rho using only order n² rounds of single qubit measurements. All right, so let me give you some more comments about this. So the lab state here is arbitrary. It could be pure or mixed. We don't know anything about it. And this order n² sample complexity applies to hard random target state psi. So typically these are highly entangled states, and they have exponential circuit complexity. So for such highly complicated states, still you only need order n² simple single qubit measurements to kind of compare it with another state. And this also gives you a sense of what I mean by almost all in the statement of the result. What I mean is that under the Haar measure on n-qubit states with high probability, any state requires order n² sample complexity. The other nice thing about this protocol that I haven't described yet is that after each round of measurement, you only need to look up 2 amplitudes of the target state. And then there's some simple post-processing you do to certify if these 2 states are close or far. Okay, so this to some extent answers these goals that I mentioned earlier in the affirmative. But one thing is that we're talking about Haar random states, and you can ask what if my target state, the state psi, is not random? It's like a structure. It's coming from some specific family of a state. then can we still like certify it or not, even if it's highly entangled? So to answer this, I first need to introduce a quantity known as the relaxation time. And to define this, let's take the target state and measure it in the computational basis. So every qubit is measured in the z basis. So you get a distribution, we call it the measurement distribution, and I'll denote it by pi z throughout the time, z being an n-bit string. So we are going to think about this distribution, this measurement distribution, as a distribution over the Boolean hypercube. So Boolean hypercube has 2 to the n vertices, and each vertex is an n-bit string. And each vertex has n neighbors. Each neighbor differ exactly in 1 bit with respect to the vertex you're interested in. So for example, when n equals 3, the all zeros vertex connects to 3 other vertices, 0, 0, 1, 0, 1, 0, and 1, 0, 0. So in general, this gives you a very symmetric and well-connected and expanding graph. And we're going to think about the measurement distribution as the stationary distribution of a random walk on this graph, a classical random walk on this graph. So what do I mean by that? So the random walk is performed in the following sense. Take a vertex, so z0, for example, randomly choose one of its neighbors. So here I've chosen z1. And with the probability proportional to pi of z1, jump to that vertex. With the probability proportional to pi of z0, stay where you are. And for these to make sense, we have to normalize them. So these probabilities are the transition rules of this Markov chain or random walk. So then you can assume, you're performing this random walk. You jump to neighbors. Sometimes you stay where you are. You jump to neighbors again. And in the limit of large number of steps, this induces a distribution over the vertices. This random walk induces a distribution known as the stationary distribution. And the time that it takes for the random walk to relax to this stationary distribution is called the relaxation time. And I'll use tau to denote this throughout the talk. One thing that I should mention is that with this particular choice of transition probabilities, it's not hard to show that the stationary distribution is the measurement distribution. So, in summary, for any target state psi, you can assign a relaxation time to it in the sense of this random walk that I just described. Okay. So let's take this and go back to the question that I mentioned earlier, that we want to certify target states that have the structure or like that they're coming from some specific family of states. So it turns out if you have such an n-qubit target state psi, and you know that its relaxation time is tau, then you can certify it. You can certify its overlap with an arbitrary state row using only order tau rounds of single qubit measurements. So here I'm assuming that you can perform single qubit measurements in arbitrary directions. If you restrict yourself with performing Pauli measurements in x, y, or z basis only, then you need quadratically more measurements. You need order tau squared rounds of measurements. But it turns out that then your protocol, your measurement protocol, becomes offline in the sense that it doesn't depend on the target state. An experimentalist would go to the lab, they would perform a certain set of single qubit measurements on the lab state row. And when they're done, we reveal the target state to them. And they're still able to say if the target state is close to the lab state or not. So the connection between this result and the first one is that it turns out for Haar random states, this relaxation time that I defined is bounded by order n squared, n being the number of qubits. And going back to our previous question, if you have a structure set of a state, it turns out for a variety of such states, this relaxation time is still polynomially bounded. So examples are like quantum phase states that I'll show you later. The ground state of a wide array of Hamiltonians, and states that look like the GAC state, for example. In all these cases, the relaxation time is polynomial in the number of qubits, and therefore your certification is using only few number of copies. Okay, so these are the main results. And now let me tell you what the protocol is. So the general idea, like the one sentence summary, is that to compare the lab state and the target state, you're going to do this one qubit at a time. So you're going to compare these two states locally, and then you're going to make a guarantee about their global overlap or fidelity. And this protocol that we use is called, we call it the shadow overlap protocol for reasons that will be clear soon. And before telling you the correct version of it, let me first try a naive one that doesn't work, but it's insightful, hopefully. So, to go with this idea of locally comparing the states and then globally saying something, the naive thing you can think of is that for each copy of the lab state, pick a random qubit, let's say qubit k, and then compare its state between the lab state and the target state. And then do this for many random qubits across many copies. And if these reduced density matrices matched between the target state and the lab state, then you can claim that, well, they have to be globally close to each other. The problem with this is that it doesn't work. And the reason is if qubit k is entangled with the remaining n-1 qubits, its reduced state is going to be very close to maximally mixed state. So, there is no information or signal here to compare between the two states. This just doesn't work. But our protocol kind of fixes this. And the trick is that instead of comparing the state of qubit k, you're going to first measure the remaining n-1 qubits in the standard Z basis, in the computational basis. And let's say this returns a configuration of zeros and ones. And now you're going to compare the post-measurement state of qubit k between the lab state and target state. So it turns out now this statement I made earlier is not the case anymore. The state is not maximally mixed. It's different depending on the choice of your state. So how do we do this? How do we compare the post-measurement state between these two states? So let's first do it on the lab state. So to do this, we take this qubit k and we measure it in a random Pauli basis, random x, y, or z basis. And this allows us to extract what's known as the classical shadow of qubit k. So by that, I mean, let's say this Pauli measurement returns the state S. So depending on the basis, this is either 0 or 1 or plus or minus or something like that. Then we're going to classically construct this operator 3 times S minus identity. And this is called the classical shadow of qubit k. And the nice thing about this slightly weird-looking operator is that it's an unbiased estimator of the true density matrix of qubit k, in the sense that if you repeat this measurement over and over and average this operator, it gives you exactly the density matrix of qubit k. Okay, so now this is on the lab state side. Let's go to the target state. And it's very easy to see that by querying the target state twice, looking up 2 amplitudes of the target state, you can classically construct this single qubit state, which is exactly the post-measurement state of qubit k conditioned on the measurement outcomes. So to do this, all you have to do is to query with 2-bit strings, Z0 and Z1. And these match the measurement outcomes on n-1 qubits. On the remaining bit, the case bit here, you either choose 0 or 1. And then if you think about it, this state gives you the post-measurement state. All right, so now having these two, all we do is that, again, classically and very easily, because these are all single qubit operators, we are going to compute the local overlap between the state of qubit k on, predicted by the lab state versus the target state. So this is the quantity that we compute. And then we are going to repeat this many times over fresh copies of the state row. And again, each time we query accordingly to figure out the prediction by the target state. When we average over these local overlaps, we get something that we call the shadow overlap quantity. And this is the output of our certification protocol. Okay, so far I've described the protocol and I've told you what it outputs. But the connection between this and the fidelity or the overlap, the global overlap between the lab state and the target state is not clear. So this is what we're going to talk about next. And the good news is that it turns out this shadow overlap actually very accurately tracks the global fidelity. And what do I mean by that? If this shadow overlap that you measure in our protocol is close to 1, then this implies that the global fidelity is close to 1. So here, tau, again, remember, is the relaxation time of the walk induced by the target state. And if the global overlap is close to 1, then it has to be the case that the shadow overlapping measure is close to 1. So if you think about the right choice of parameters epsilon and tau, this suggests that these two quantities are just going to be very close to each other. They're going to closely track each other. So this is why it works. And to give a sense of the proof of this fact, let me give you like a different perspective of the measurement protocol I just described. So instead of thinking about these single qubit measurements and like this back and forth between the target state and the lab state, you can think of all this that I described as measuring the expectation of some observable L. So this observable L, and this is the shadow overlap. So this observable L depends on the target state, and it's basically an approximate projector onto the target state, in the sense that if you apply this operator on the target state, it would leave it unchanged. If you apply it to anything orthogonal to the target state, it would shrink it. And the amount that you shrink relates to this relaxation time of the target state that I defined earlier. So one other way of thinking about this is that if you take the identity minus this observable L, it acts as a Hamiltonian. The unique ground state of this Hamiltonian is the target state psi. And the non-trivial fact about this is that it's gapped. The gap of this Hamiltonian is 1 over the relaxation time. And the other non-trivial thing is that this Hamiltonian is not local, because we know that how random states can't be the ground state of a local Hamiltonian, but it's sparse. And this allows you to measure it efficiently, the way that I described with these single qubit measurements. So you can think of all this like shadow overlap protocol as a way of measuring the energy of this sparse Hamiltonian. And if you get something close to the ground state, you had to be close to the ground state. If the energy is close to the ground state energy, sorry, you have to be close. If you're measuring something that's high energy, then you're probably far from the ground state. And the fact that this operator exists again relates to this random walk that I defined earlier. This operator L is just some sort of normalized transition matrix of a random walk, if you're familiar with it. And that's why the gap of this Hamiltonian or this observable is related to the relaxation time. Okay, so this was the protocol, and it gives you these nice scalings with a number of qubits, and like allows you to certify highly entangled states. But it also has like a diverse set of applications that I'll briefly go over them. But before that, let me again stop. Is there any question?
So, hear me?
Yes.
Okay. I kind of wondering the relaxation time is determined by the target state, right? So it is you must know its distribution exactly, so that you can design the random walk and you can design the relaxation time. Is that the case?
Yeah, that is the case. But note that for almost all quantum states, we know roughly what this relaxation time is. It's bounded by order n squared. So there are like specific states that are not hard random. For those, you kind of have to know what's going on. So we showed this for many families of states that you can like analytically know what the relaxation time is. And we have a framework in our paper that you can apply to other states. But in general, you can think of states for which finding a relaxation time is not easy. Maybe like it's hard to both computationally and analytically to find.
So you mean it's hard to find, but you can guarantee that it is like within the relaxation time is n squared. That's your claim.
So with high probability, so if your state is like random looking, then with high probability, like exponentially high probability, sorry, with all but an exponentially small fraction of states, the relaxation time is bounded by n squared. But like I can construct the states that are not random. They fit into that small like part that not covered by this exponentially small. They're part of that exponentially small fraction. So for those, you have to know what the mixing time is.
I see. So so you can basically design a transition matrix, which is kind of a projector to the target state. And this also gives you a Hamiltonian. So if the state is highly entangled, what will the Hamiltonian look like? It's also guaranteed to be gapped, even it is highly entangled.
Yes, that's that's the material part. That even if you have a very highly entangled state, like a high random state, that there is still a gap.
I see. Okay. So sorry. Another question is about the when you compare the measurement locally. So for qubit k, and you need to fix all other qubit, or you just need to fix some other part of the qubit in the overlap protocol.
Yeah, so you have one copy. You do this one copy at a time independently. For each copy, you choose one qubit randomly, and then you measure the remaining one in the Z basis. And for each copy, you do the same thing. So in particular, this protocol doesn't need you to somehow post-select. So you don't have to only take outcomes of particular measurements. Like you just perform it. Like each time randomly it projects you into some subspace, that's fine. When you average over that, you can still say something about the global fidelity.
So
is that basically like your question, or did I not answer it?
Yes. So for each measurement time, you just randomly select some subset, and you just perform the comparison at this measurement, and you average all of them. So is there any portion of the qubit? I mean, how much percentage must be fixed, and how is the qubit k be fixed within some number, or it can take some fraction of the whole qubit number?
Yeah, so you actually have a hierarchy of these protocols. In the first level, you choose one qubit, put it aside, and then you measure the n-1, all of them in the Z basis. In the second level, you choose two qubits and put them aside, and you measure the remaining n-2 in the Z basis and so forth. And it turns out that there are states, and for each of these, again, the number of measurements that you need to perform relates to the relaxation time. The point is that depending on the number of qubits that you put aside, the relaxation time differs. So there are states that you can't verify or certify with just qubit k being 1 qubit, but you can do them if you can certify them if you choose 2 qubits and measure them randomly.
Okay, I see. So when you apply the hierarchy, is like a step by step, or you just randomly apply the hierarchy?
Yeah, so you just choose the hierarchy. You like you choose one level, and then you go with that. And then you hope that like for that hierarchy, the state that you have in mind, the target state that you have in mind, for that particular level has good mixing time or has good relaxation time. So one example, maybe that would clarify, is the GHZ state in the X spaces. So apply Hadamard on the GHZ state. So it turns out that you can't verify this with level 1, but you can verify it with level 2. And the reason is that the relaxation time is really bad in the first level, but it's good in the second one. But you have to kind of like know this. There's no like procedure for figuring which level of the hierarchy to use.
So you must know which level has no relaxation time. So you must know the exact description of the target state beforehand.
Yeah, this relates to your earlier question that for most states, the relaxation time of level 1 is fine, but there are worst case states for which you need to have this additional information to be able to run this protocol. Like otherwise, you wouldn't be able to.
I see. Okay. Sorry for interrupting.
No,
thank you.
Very good question. Okay, so if there are any other questions, let me go to the applications. And let me start with benchmarking. So here, the lab state is something prepared by a noisy quantum device. And the target state is the ideal state that we wanted the device to prepare. And our goal is to certify that the fidelity between these two states is large. So this would tell you that the device performed correct, the correct operation. The problem is that measuring the fidelity or the global overlap is statistically challenging. It requires exponential resources. And we want something very simple that you can actually run on like noisy devices available in near term and all. So naturally you can think of applying our protocol. And this is something that we've numerically checked for 20 qubit target states. So I'll give you different setups, different numerical experiments. The first one is when the target state is a hard random state. So you randomly pick a 20 qubit state. And then you apply a white noise on this state. And by that, I mean a global depolarizing channel. So that gives you the state rho. And then you look at the overlap between these two. So the chart that you see, the plot that you see, on the x-axis, we are increasing the amount of noise we are adding. And on the vertical axis, we're tracking the actual fidelity, the one described by cross-entropy benchmark that I introduced, this heuristic method, and the one coming from our protocol, the shadow overlap. And as you see, all of these going to match each other. They're very closely following each other. You get a good estimates of the actual fidelity by performing either cross-entropy benchmark or our protocol, which are much simpler to do in experiments. You can do this by taking the hard random state as your target state. And now instead of the white noise, you apply coherent noise on top of that. So by that, I mean you take the amplitudes of your state and add small Gaussian shift to the phase and the magnitude parts of your state. So that's what our model of coherent noise. And here you start noticing that the cross-entropy benchmark in the high noise regime is not giving you accurate predictions, but still shadow overlap and fidelity are very close to each other. So things get more interesting if instead of a hard random state, you take a structured state. So take a product state over 20 qubits, and each of these psi i's are just simple single qubit states whose amplitudes are randomly chosen. And then to give them complex phases, apply a random, operator U phase, which gives you, complex phases on all your amplitudes at random. So it's structured, but also the parameters are, chosen randomly. And then add white noise as before. And as you see now, the cross-entropy benchmark is not performing well. It's kind of like underestimating the fidelity. Shadow overlap is closely tracking. And this performance is more, you can see it more clearly if instead of white noise, you add coherent noise. Now cross-entropy benchmarking is completely giving you off numbers. And this is because, as I mentioned earlier, it kind of like it's a heuristic method that doesn't care about the phase component of your amplitude. It only works with the magnitude part. And here, coherent noise exactly is, tweaking the phases. But shadow overlap remains faithful. And, the conclusion is that you have this method with, very experimentally friendly requirements and rigorous guarantees that you can use instead of fidelity for benchmarking purpose. So this was the first application. Let me now move on to the second one, which is about optimizing or training quantum circuits. So here we have a parameterized quantum circuit, which you can think of these parameters describing the gates that you apply in the circuit. For each set of gates, we get some state. This is our choice of the lab state row here. Our goal is to find the right choice of parameters, the right ordering of gates, such that this state prepares a target state psi we have in mind. And as before, you can think of this as an optimization problem, where you change the parameters to maximize the fidelity between the target state and the output of the circuit. Again, finding fidelity, estimating the fidelity statistically is hard. And this optimization part is also challenging. So what happens if you apply shadow overlap protocol, our protocol to this? So we numerically check this. So our choice of the target state is a matrix product state. And this matrix product state describes a state which is prepared by an IQP circuit plus T gates. Okay. And what we want to do is to come up with a circuit involving Hadamard controlled Z and T gates, like a universal gate set, that quantumly prepares this matrix product state for us. And there are two numerical experiments that we have done. In the first one, I'm going to assume that we already know the right ordering of the gates to apply. So we know the circuit that prepares the MPS. What we're going to do is to apply the gates one by one and track how the output of the circuit, what's the overlap between the output of the circuit and the MPS we have in mind. Naturally, the more of the gates that we apply, we should get closer and closer to the MPS. And this is exactly what you see. As you apply more levels of gates, the shadow overlap, which is the y-axis, linearly increases. And this is for a 50 qubit experiment. So in this sense, this is the shadow overlap part. Let me now tell you what happens if instead of shadow overlap, you check the fidelity, the global overlap between the output of this circuit, this partial circuit, and the MPS. So if you do this with fidelity, you see that it doesn't change until almost the end of the circuit, and then it jumps from 0 to 1. So very different behavior. And this is known as the barren plateau phenomenon. And this is a problem with using fidelity. It has like a very weird landscape. It's pretty much flat for the most part. And then when you get very close to the target state, it very sharply jumps. Whereas our shadow overlap is behaving more what you expect intuitively, that, as you have more gates, things should just linearly get closer and closer. And this is like something like how the classical Hamming distance between two n-qubit strings behaves. As you change the bits that differ from some other bit string, you linearly decrease the Hamming distance. I know this is something nice for optimization purposes. This is the type of behavior that we'd like to see. And now you can actually, instead of assuming that you know the right order of the gates, you can assume that we want to find the right set of parameters. We want to find the right order. And there are two plots here. The first one, we're kind of like optimizing. We're choosing different set of gates. And for each one, we're checking if we got the right MPS or not. And as you see, the optimization is very nice. As you increase the number of steps, you get closer and closer to preparing the right matrix parallax state. This is the shadow overlap. If you try to do your optimization with fidelity, it doesn't make progress. It's kind of like performing some weird walk in the optimization landscape. It can't really find the right set of gates to apply. And this is exactly because of this behavior that I described, this barren plateau issue. Okay, so this was the second application. Let me tell you about the last one, which is about the tomography of quantum states. So here, the lab state is some unknown quantum state. And our goal is to learn a classical description of this state. So this classical description is in terms of a machine learning model with some parameters data. So here I'm going to fix a classical neural network. And the way that this neural network represents a quantum state is the following. You give it an n-bit string as input. It goes through a network of neurons and it calculates a complex number. You're going to take this complex number as the amplitude in the basis vector x. So this is an example of a query access we had earlier. So the neurons have a set of weights, and we're going to collectively denote that by theta. What is our goal? Our goal is to find the right theta, the right neural network, in the sense that it has the highest overlap with the lab state row. So in this sense, we perform tomography or learning on the state row. So there are two problems with this. Generally, training neural networks is heuristic. And oftentimes, they kind of like hallucinate things in the data that doesn't actually exist. And this motivates the problem of certifying it. You train the neural net, but it's important to check at the end if the classical model you get is close to the unknown state row or not. And this is what we do. Our choice of the unknown state that we want to learn is a random binary phase state. So this is a state where the magnitude part of all the amplitudes is the same. It's 1 over square root 2 to the n. But you assign a random plus minus 1 phases to each amplitude. So we have 120 qubits in this experiment. And it turns out if you truly at random choose these phases, this state in a formal sense is indistinguishable from our random states. So it's quite entangled. Yet we want to perform tomography on it and have some sort of neural net that learns the phases phi x of this state. So again, we have two parts. We have to train a neural net, and then we have to certify it. So we use single qubit measurements for both training and certification. In the training part, this is a heuristic method called stochastic gradient descent, which kind of tunes the parameters of the neural net such that the state described by the neural net matches the prediction coming from our single qubit measurements. And this matching is measured by this loss function on the y-axis. So the smaller the loss, the closer the output of the neural net to the measurement data coming from the lab. And as you see, as you increase the number of gradient steps, as you keep tuning these parameters, at some point your training jumps from having a high loss to a very small loss. So in this sense, the training has been successful. It has learned the right choice of parameters. And you can actually certify this. You can use our protocol, the shadow overlap protocol, to see that after this threshold, the overlap between the unknown state and the neural net jumps to 1. So they're very, very close to each other. And there are other nice things you could do. Once you have this neural net representation of your quantum state, you can measure non-local properties, things like the purity of a subsystem. So it turns out that this requires exponentially many single qubit measurements if you want to directly do it on the lab, the lab state. But if you rely on this learned neural network, you can actually provably do it efficiently. And we numerically show this. This plot has the ground truth, the actual purity, and the data points are what the neural net predicts. So it's matching our expectation. Okay, so in summary, I presented this shadow overlap protocol, which relies on very simple single qubit measurements on a few copies of the lab state. And this is when you have query access to the target state's amplitudes. And it kind of satisfies these properties that I mentioned earlier, and has many applications. So just to summarize the applications, shadow overlap allows you to do benchmarking in the regime that the cross-entropy benchmarking is successful, but also it applies when the cross-entropy fails. For optimizing quantum circuits, the fidelity suffers from the barren plateau, but for many quantum states of interest, shadow overlap has this nice Hamming distance behavior that allows you to perform the training. And you can also use this shadow overlap protocol to train and also to certify neural net representation of quantum states. So that's almost it. Let me briefly mention some open questions. The first one is, what families of states have polynomial relaxation time? So I mentioned how random states do that. And we have a list of the states in our paper that we prove polynomial relaxation time for them. But we still don't have a good understanding of, when is this possible? The other question related to this is that our protocol kind of shows you can certify almost all quantum states, but we don't have counterexamples that we can't certify with few single qubit measurements. So are there states that, no matter what basis you think of this state in, there is no way to certify it with performing single qubit measurements. You have to consider entangling measurements. We don't know the answer to the question. And finally, in the whole talk, I assume that we have efficient access to the amplitudes of a state. And in general, this is not something possible. We have exponentially many amplitudes. So what are families of quantum states that admit concise representations? There is like a classical model that runs in polynomial time in the number of qubits. It takes x as input. It outputs psi of x. What are these families? And one way to formalize this is to ask what families of quantum states admit efficient representation using neural networks in the sense that I described earlier in the talk. I have some upcoming results about this, so watch out for that. Very briefly, it connects to very interesting physical properties of your state. Whether the question whether you can have efficient query access or not has some interesting connection to like the types of correlations that you get in your state. Okay, so that's it. I thank you all for your attention.
Okay, thank you very much, Mehdi, for a very clear and very informative talk. Okay, so this is the part where we officially have like the questions from the audience. So if you have any questions, please unmute yourself and you can just ask directly. You can also just give comments if you want. If you have no particular questions, that's also fine. Okay, so maybe I can ask first if no one is asking. So for when you do the protocol, so for each round, let's say you choose one qubit, right? Like qubit K. and you do this measurement on the remaining n-1. So is sort of the analysis that you're doing you can do for 1 qubit at a time, or you would have to test for many qubits before you sort of actually compute sort of a proper shadow overlap? How does this work?
Yeah, so you do it for every single round of measurements. You don't wait for any like particular measurement outcomes. You choose your qubit randomly. You measure the rest. Depending on the outcome, you query the targeted state and you compute the shadow overlap. And then you average over it for many rounds. So that's
Okay,
maybe
but
the kind of like the, yeah, go
I
ahead.
guess like what I wanted to really ask is like, so I can even just like look at a particular qubit, and if already the overlap is very far from the target, you can immediately conclude that it's far. You don't even need to test the other qubits anymore. Is that the sort of thing that you?
Yeah, that's correct. Yeah, I guess we didn't quite consider this, that at some point, okay, so I mean, there's a trade-off. If you want your protocol to be offline, in the sense that it works for many targeted states, then you do have to measure these rounds of order n squared or something, rounds of measurements. Then I can give you a bunch of targeted states, and for each one, you can answer the question. If you're allowing online protocols, meaning your measurements depend on the choice of the target state, then you can things like you mentioned. You can get smarter about how you do the protocol.
All right, so I'll let somebody else ask questions.
Yeah, thank you for the very nice talk. So I kind of don't understand why the optimization quantum circuit can avoid the aberrant Pareto problem. You randomly select some, you assume you don't know the order of the circuit, and then you apply them, each part of them, and then how do you do that?
Yeah, it's a bit weird that this is true actually, but I think the intuition is this Hamming distance that I mentioned. So if you take, yeah, so there are very simple examples of states that I can write down, targeted states. Like, for example, plus to the n. So all of the qubits are in the plus state. And if you just write down what this observable L that I described earlier is, it's exactly the Hamming distance between this, or it's like computing the Hamming distance in a sense. So it's like the fact that this is like a Hamming distance doesn't have to do with the particular way that we perform the measurement. It's just true that a shadow overlap is a more forgiving quantity compared to fidelity. If you flip 1 qubit in the all plus state to minus, fidelity goes to 0. The overlap is 0. If you do that for a shadow overlap, it just slightly decreases. So it's like, because you're randomly picking qubits and looking at the local state in order to find shadow overlap, there is like a good chance that you miss these little things that like are going wrong elsewhere. You get like a better view of how the two states really look like each other. With that being said, there are also states that shadow overlap has this baryon plateau phenomena. Maybe I should have been more clear. Like, if your state is highly entangled, then shadow overlap behaves similar to fidelity. It does have this baryon plateau phenomenon. But it turns out there is a large class of states with no global correlations, for which fidelity is still a pretty flat landscape, but shadow overlap behaves nicely, like Hamming distance.
I see. So yeah, probably that's because you have the local behavior that can still not too worse if you apply the overlap shadow protocol. And I'm not sure why. So you mean you randomly pick different qubit, but how about different depths? Why you draw the figure with different color of the depths? You mean you just optimizing different part of the circuit? What was the?
So here, what I mean is that if you suppose I was here, I had applied all the gates correctly, then obviously I'm preparing the MPS. But what I'm doing now is I'm taking some of the gates out. And then I look at, so I'm not applying the orange part, I'm just applying the blue part. So this does prepare some state. And intuitively, what I expect is that this state is just slightly far from the actual MPS. So this turns out not to be the case if you're thinking of fidelity. Like even a single poly X completely makes your fidelity go to 0. But for shadow overlap, if you look at this figure, as you apply gates, you kind of like gradually get closer and closer to the target state. So this is a nice behavior if you don't know the correct order of gates. If you want to like optimize, because then you know that you're making progress. Whereas if you just look at fidelity, you don't know whether you're making progress or not. You're always measuring 0.
I see. So you have the protocol over the protocol. You can just run. I mean, step by step, growing your fidelity and estimate the state that you want. Yeah, I'm optimizing it. Yeah. Okay. Thank you.
Welcome.
So, you have more questions?
I'm just wondering, when you say about the open question, you say not every state is known for their relaxation time. You mean now people just don't know the condition of when the relaxation time is poly n, and they are so do we have some example that the relaxation time is large or exponential? Do we have this example?
Yes, there are very simple examples where the relaxation time, I guess, is infinite. One example is the GHZ state in the Z basis. So it's all zeros plus all ones. If you think about it on the hypercube, it's just two disconnected points. There is no random walk that starts from here and like, with local jumps, you can't get to all one. So there is no relaxation time there. I guess it's like, but if you change your basis from the Z basis to the X basis, it turns out that GHZ state now, instead of all zeros and 1s in the plus minus basis, it's the uniform superposition over even Hamming weight n-bit strings. So all zeros, and then it has 2 1s, and it has 4 1s, and so forth. So now if you think about this distribution, it's quite uniformly distributed over the hypercube. And therefore, there's like a random walk that just like makes local jumps, and it kind of uniformly covers the whole cube with polynomial mixing time. In fact, the mixing time you can actually bound is n/2, n being the number of qubits. So for many of these examples that we have thought, just applying a local change of basis seems to fix the problem. If the mixing time is bad in one basis, when you change it locally, like Hadamard or other basis changes, you can recover a good mixing time. And that's fine because experimentally I can easily apply local change of basis.
So this is also the reason that your protocol can work for almost all the state, right? Because you apply the random poly measurement change basis, I think.
Right. So you can think of like how random measure is invariant under local change of basis. Yes.
I see. Okay. Thank you.
You're welcome.
Okay, so I think like I will sort of like end the recording for this talk, but if people still want to ask questions, I guess they can still remain and ask questions.